conservative. As you get more and more familiar with these, there are shortcuts that you can take. I'm gonna try not to take shortcuts to start out with. At some point, I might start doing it. So if I have my initial energy is equal to my final energy, and I have two types here, because this is classical physics. And I did not mean to put that there. What are my two types of energy?
Conservative energy and conservative energy and non-conservative energy. Not that
There's
much.
such thing as conservative energy.
Potential and kinetic.
There's the ones.
Oh, okay.
So I have kinetic energy plus my potential energy initial is equal to my kinetic energy final plus my potential energy final. I'm about to ask the question, so get yourself psyched up for it. Chorus of angels. What's the formula for kinetic energy?
1/2 mv squared.
Doing it in rounds, I see. Okay. 1/2 mv initial squared, and that is
We wanted to do a little variation.
I will expect orchestral accompaniment next time. All right, what's the formula for potential energy?
Which one?
So, like you mean it.
Which one?
There we go. The one associated with weight.
MGA.
Now, if you want to put in the plus C, you can. It'll just cancel out immediately. All right, so we've gotten it down to this far. This is sort of generic steps. So there are a whole lot of energy problems. Once you establish energy is conserved, you got kinetic plus potential equals kinetic plus potential. You write down the formulas, one for each of the potentials involved, and then kinetic, which at some point you will know by heart, like you know your own name. Now let's see what we can get rid of. Is there anything we can get rid of?
And
All right, we do have a common factor to every term. Anything else we can get rid of?
well, if we move like the potential energies together and the kinetic energies together, we can cancel it out. So never mind. That's just too much work. Wait.
What's equal to 0? We're specifically solving that problem over there.
Oh, yeah. Yeah.
Oh, you said VI?
Yeah.
0 because VI equals 0. The initial speed is 0. Anything else we can get rid of?
We can plug in VF.
We're going to solve for VF, so we'll assume that we don't know it's 19.8 meters per second.
G is negative 9.8.
H is height and
Yeah, so 30.
H height and right?
I only caught part of what you were saying.
H is the height initial and then height.
Okay, so you already plug numbers in?
No, I'm just curious if that is correct.
Divided by G. This term doesn't have G in it, so we could divide by G, but I don't think it's going to get us anywhere.
Can we use this? Oh yeah, we can use displacement on the H's, right?
Meaning,
So
We
if
use the actual
the
initial.
final is 0.
Right.
Sorry. No, go ahead.
so I can hear one of you go.
I guess, do we plug in the ones that we have over here, like 30M being the initial height, 10M being the final height?
Do you want to?
I guess.
What I was thinking was if we use our displacement numbers, so we started our initial height would be 20 and then our final height would be 0? Would that work?
Make the initial height what again?
20, and then the bottom be 0? Would that work? Or would that change our whole calculation?
Let's find out.
Oh.
All right, so going with Giovanni's suggestion, we have, I'm gonna put this on Earth. No, we've already done Earth 1. So 9.8 times 30 is equal to 1/2 VF squared plus 9.8 times 10. This is 29.4, this is 19.6. Subtract it, I get 9.8.
Because it's G.
Oh,
instead of
wait a second. Times 30, that's 294, 196. So 98 is equal to 1/2 VF squared. VF squared is 196. VF equals, I'm thinking somewhere around 19.8. That, am I feeling right?
196, it's just 14.
So-
It's
Did
14.
we make a mistake over there? Or did I make a mistake over here?
9.8 times 30.
I'm sorry, we're looking for VF,
Yeah,
but
Divided by.
I messed up somewhere. All right, so we set that equal to 0, that's fine.
You did
Um,
something weird at the 1/2.
20, so that's 4, 392.
You put
Yeah.
98.
Wait,
Yeah, you put
1/2
98 first, and
VF
then-
squared, and it's actually 196 equals 1/2
Yeah.
VF squared.
oh,
That's
You
what.
flip-flop
Yeah,
the
you
things.
flip flop the answers.
So
So that
Oh.
would be 294 minus
That's-
98.
that's 98, that's 196, there we go.
Yes, yes,
Thank
yes.
you. 392. Another one for the blue. So VF should be somewhere around 19.8.
Yeah, that's actually right.
All right, so obviously plugging the numbers in based on what we have over there, fine. Robin was suggesting we do it slightly differently. We do the initial height to be 20
And
and the
then.
final height to be 0.
Yeah.
So if we did that, so if we made that 20 and that 0, we would end up with, well, that's 196 is equal to 1/2 VF squared. And we are now at that point. And this goes to a comment I made earlier, the fact that because you can always add a constant to make the values, you can make 0 anywhere you want. So where we had 98 times, I don't think I gave a mass actually. 98 times the mass is the potential energy relative to the ground at the end. I could always add some constant to make that 0. So that plus C really allows us to make 0 anywhere we want. So the simplest way is to make 0 either at the beginning or the end. Make that 0 or make that 0. If you like the math, you can make pretty much anywhere 0. But if you want to simplify it and spend more time thinking of great thoughts, I would recommend making this 0 or that 0. Now, if we made the final height 0, so if we said that was 0, because we say so. What would the, oh wait, no, that's not the one I want, sorry, scratch that. If I want to make the initial height 0, what is the final height?
-20.
Suppose I made down positive, what would the final height be?
20 meters.
It'd still be -20. When we're dealing with vectors, we decide positive and negative direction and live with it. When you are dealing with energy, this height is going to be a bigger number than the height below it. It is already built into it, the fact that the conservative force is acting down, it's already built in that this has to be a smaller number than that. So So if we made the initial height 0, the final height would be -20, regardless of what direction we said was the positive direction. Questions before we make it seem more difficult?
I'm trying to think of it. So for all of these formulas, are these only for one object or do we use them for a system?
Yes. All right, so typically in 151, you would consider I would use 1/2 mv squared for all masses that will go in the same speed. For MGH, it would be all masses that were at that particular height.
Okay.
If you want to use it for a system, well, in fact, it is a system. I have a rock there that has some mass. It's composed of a whole bunch of tiny little particles
Yeah.
that we're all lumping together and calling it one thing.
Okay.
So, and if you get far enough in physics, what you end up doing is a whole bunch of, you use the sum of a very large series. So you're not dealing with numbers at that point, you're just dealing with letters, but sigma shows up a whole lot because you're adding up the kinetic energies of each tiny little particle. Yes, Alan?
I gotta go. I feel
Okay.
yeah.
I didn't realize what I was saying was so controversial, but, you know.
No, you haven't
Okay,
caused
okay.
one yet.
Now, once Alan is gone, I'll tell you the answers to the test.
Okay.
Oh, wait, yeah, that's actually how that works.
All right, other questions?
Music's so cold.
The class after this, which has more people in it, I will be sweating. But the class before it, we do have 2 students who have a blanket.
Oh,
Oh, really? It's very comfy.
Is one
can
of
I
them
do that?
open?
You can bring a blanket in if you want. Nothing against it.
I mean,
I think the official is you cannot wear anything that would distract people from the learning process.
So not the Hello Kitty one. Good for that. Yeah. Can we bring hot?
Can you wait, what?
No.
I wouldn't recommend it. I mean, if
I-
you're bringing a blanket and a pillow, you're gonna be.
Yeah, you won't be paying attention to the class anymore.
I have had people who've had sitting difficulties and they find these chairs incredibly uncomfortable. And in essence, it's called a cushion at that point. I don't have a problem with that. Pillows, I think that if you're that tired that you need a pillow, then perhaps this is not the right place at the time, this time.
Mhm.
That's not out of the class, that means that it's just a bad day for you. All right, let's make this look harder.
Yeah.
It's not harder, I'm just making it look harder.
Oh.
10 from all the judges except the Soviet judge, who gave me a 0.
No,
That's a B.
not these things again.
a roller coaster?
Ski slope.
Oh.
I thought it was a graph.
So did I.
I thought it was just one from questions.
It looks like snowboarding just because it's a lot easier to draw. So he is delicately balanced at the top of this hill. A gnat lands on his back.
I'm sorry, what?
A gnat.
What is
Mosquito, if you wish. Gnat, just a
Oh,
tiny
gnats
little
are
right.
bug.
Ah.
A tiny little bug lands on his back, which is just enough force to get him to start to move. So his initial speed is close enough to 0.
Uh-huh.
His he's gonna be skiing down, and I wanna know how fast is he going when he gets down to here. Let's make this 50 meters on the ground. So the reason I make it snow here is because I'm gonna pretend that it is frictionless. I guess we sliding on it. Go ahead. So, first, as he's going down, I want to look at it, this position right here, when he's here. The forces acting on him. So let's do a force diagram of the man. What are the forces acting on him, her, it? I'm not quite sure how his pronouns.
There's a normal force from, okay, I need to work this on the board parallel to the ground.
What does normal mean?
Perpendicular.
Well, hold on a second. Oh,
So normal force will be perpendicular to the ground.
yeah. But I don't have to
And
word it.
gravity.
Okay, so
Down.
Yeah.
All right, so I have weight acting this way, normal force acting this way. There's no friction. Weight, the force. Conservative or non-conservative?
Conservative.
Normal force, conservative or non-conservative?
Non-conservative.
So we now have a non-conservative force in this problem, and I have to establish what is the work being done by it. What is the work being done by the normal force?
force times displacement.
Okay, so the work done by the normal force is equal to the, I guess I can write it as, I have a normal force here, not displacement. Well, let's take it that next step. At any moment, well, let's think about the normal force. The normal force right now is pointing, at this point right here, is pointing that direction. As he slides down, that normal force is changing direction. So the normal force is not a constant. So when we're doing something times a displacement, when it's not constant, we basically have to do it each step of the way. So we would do, what is the work being done at this moment, and then at this moment, this moment, this moment, this moment, and so on. Well, we can simplify that a lot, we can just simplify that by what is his, at this point right here, in which direction is his displacement?
Displacement?
Displacement.
Sorry, we're talking instantaneous. When the normal force is in that direction, in which direction is he going?
Dis-
So, going
Is
with,
it like down and then like,
yeah, eventually, but I'm talking about just this moment right here. He's
Yeah,
going that way.
parallel to
The
the.
normal force is that way.
Perpendicular to the normal force.
So therefore, what is the work being done by the normal force?
Zero.
And it is zero all the way down.
Uh.
Because everywhere on this slope, his displacement, his instantaneous displacement and the normal force are perpendicular to each other the entire time. The only way that the only other time that you would potentially wonder for a brief moment is if he's going so fast that he comes off the hill, but at that point, the work is being by the normal force is zero because there's no normal force at that point. So this is equal to zero in this case. Therefore, the only force doing any work is the force of gravity, which has been established is conservative. So I know that the non-conservative work is equal to the change in energy. Non-conservative work is zero because they are perpendicular to each other. It's equal to E final minus E initial. Therefore, my initial energy equals my final energy. And this is exactly where we were before. What are my two types of energy?
Potential kinetic.
What's the formula for kinetic energy?
1/2 mv squared.
Like a single voice. That was spectacular.
Yeah.
Sadly, did not sound like the Course of Angels. Formula for potential energy?
Which one?
The one associated with that conservative force of weight.
mgh.
This will look very familiar.
Wait, I'm sorry, we would just give Dr. Fox a moment to appreciate his handwriting?
Oh.
I know, like,
It's crisp and clear.
That's actually, you actually.
It's been done now. I don't have to do it again. What's zero?
Well, right now, it's just,
wait.
The initial velocity should be zero.
cancel.
The initial
Because you see.
speed.
Oh, sorry.
Zero, because VI is close enough, it's approximately 0 meters per second. I mean, how much speed you can pick up when a gnat lands on your back?
We can cancel out all the mass. Should I mass?
Oh, cancel the masses out? Okay, not because they're zero.
Just because they're with everything, it's a common factor.
Yes, for each term. All right. We can set something else to zero.
We can set which, the
The
final
final
or the initial zero depending on which.
You sounded like you wanted to make final.
Fine.
Okay.
Because Giovanni said so. Actually, it's zero because h of f is equal to 0 and h of f equals 0 because Giovanni said so. All right, so we've now reduced to a very simple formula. The acceleration due to gravity times the initial height is equal to 1/2 vf squared. It's trying to solve for vf. Vf is equal to the square root of 2gh initial, which is the square root of 2 times